We've been solving the linear system ax equals b by hand. So when you do this process by hand, you use the Gaussian elimination algorithm, and you take this matrix all the way to what we call row-reduced echelon form. Now, all of that is great if you do it by hand, but ultimately, when people apply linear algebra in the real world, they have to solve these systems by computer. Now, this row-reduced echelon form takes about, in the long run here, we say 2/3 n cubed operations. And this is for a square matrix of size n by n. So if you have n sufficiently big, it's going to take you about that many steps as a rough estimate. Now, if you want to solve it by computer, you have to essentially train the computer how to do this process, how to do the row reduction process. Now, we've already discussed that row reduction can be implemented by elementary matrices, and that means it's basically a matrix multiplication problem. So what we're going to do here is we're going to delve a little bit more deeply into this idea and come up with a more efficient way of solving not just one linear system, ax equals b, but lots of linear systems. And we need a new idea for this. So we're going to use this idea for another approach. And effectively, I'm going to introduce the idea first and then show how it works in the next video. Okay, so here's the idea. We're going to talk about something called a matrix factorization. And if we take some matrix, to factorize it means you can represent it as the product of some other matrices. Now, for Gaussian elimination, we are going to pick one. It's going to turn out, that there's one specific factorization of a matrix. It's going to be A is LU, where L is a lower triangular matrix and U is an upper triangular matrix. Now, we've discussed lower and triangular matrices before, but effectively it's a statement on their non-zero values. So if you have a matrix with non-zero values, they'll kind of organize themselves this way. Any non-zero values that appear in a lower triangular matrix are either on the diagonal or below the diagonal, and any non-zero numbers in an upper triangular matrix are either on the diagonal or above it. So this is going to be our goal. We are going to try to reduce A to some upper triangular matrix, not the full row-reduced echelon form, and we'll see what comes out of this. And bear with me as we work through this. Once we get to the end result, I will then explain to you how this factorization helps us. So we're going to take a specific example here. We'll take this matrix, a 3x3 matrix, and all the ideas that I'm going to demonstrate to you will be in the context of this one example, but rest assured they are generalized to many other square matrices. So the goal here is to reduce A to an upper triangular matrix. So the first step that we need to do is realize, okay, we've got a pivot in that top left position. Let's create zeros underneath it, and we're going to do it with elementary matrices one step at a time. So that means we need to take two bunches of row 1, add it to row 2 to create the new row 2. So the reduced or the row equivalent form here will have the same top row, the same bottom row, but now we're going to create a 0 underneath that first row. So we'll take twice of the first entry, add it to the second, 0. Twice of that top entry, add it to the next one to make a 1. Twice of this entry makes a 0. Now, the elementary matrix that performs this is essentially us just doing this same step on the identity matrix. So we'll have a 1, 0, 0, a 2, 1, 0, and a 0, 0, 1. So we continue. We're trying to turn this resulting matrix into an upper triangular matrix. Okay, so that means we need -3 bunches of row 1 added to 3 to make the new 3. So this is going to give 1, 2, 1, 0, 1, 0. And now we're going to zero out that bottom entry. Oh, sorry, we need -3. Yep, there we go. So -3 times 2 is -6 plus 7 is 1. -3 times 1 plus 4 gives us another 1. The elementary matrix that executed that row operation, we do the same row operation to the identity, and we get this, -3, 0, 1. So we're one step away here. We need to create a 0 in this position. So what we'll end up doing is -1 bunch of row 2 added to row 3 to make the new row 3. When we do that, here's what we get. 1, 2, 1, 0, 1, 0. And if we add the negative of each of these, we'll get 0, 0, and 1. The elementary matrix that did this, 1, 0, 0, 0, 1, 0, 0, -1, and 1. As we wanted here, we have an upper triangular matrix, so this thing here is our U. And the point of all of this is that we have the following. We have created this matrix U by taking 3 elementary matrices and operating on A from the left. So we'll have E1 on the left of A, we took E2 on the left of that, and then we took E3 on the left of that. Now, with matrix multiplication, those brackets are not necessary. There's a property that says you can multiply any 2 adjacent matrices in the order you'd like and then put them together. So we get this. Now, this is great, but what we're really after is a representation of A. We want to get the A by itself. So that means somehow we need to move these things over. And this is precisely the job that matrix inverses do. The question we need to answer is, are these elementary matrices invertible? And this has already been hinted at, and you could probably guess, but the answer certainly is yes. If you want to think of it on a very loose level, an elementary matrix represents a row operation. If you want to undo the row operation, you simply take the opposite operation. If you want to be a little more technical about it, let's take a look here. So our matrix E1 was of the form like this. So we're just looking at a 3 by 3 case. But if we have a 3 by 3 case, if we have some elementary matrix that looked like this, if we wanted to find its inverse, remember the inversion algorithm, right? What we do is we take this, augment it with the identity, and then we say, oh, okay, what do we need to do to reduce it to the identity on the left? All right, so if I were to take this, C1, 1, 0, 0, 0, 1, put the identity matrix here, we can see, hopefully clearly, that the only thing we need to do is to create a 0 down there. We'll take -C1 bunches of 1 and add it to 2 to make the new 2. So this is going to create the identity on this side, which is what we wanted. And as we expected, we'll get 1, 0, 0, -C1, 1, 0, 0, 0, 1. So this indeed is our E inverse. So the point of all of this, the inverse of a row replacement elementary matrix is simply the exact same matrix with the sign of that non-zero, of that other number changed. So if I have an E1, 1, 0, 0, C1, 1, 0, 0, 0, 1, its inverse exists, and it simply changes the sign here. All we are effectively doing is undoing the row operation. And this holds for all elementary matrices. I'm not proving it here, but the same argument can be applied for row swaps, for row replacements, for row scales. Now, how does that help us? Okay, so we come back to the following. We have U is E3, E2, E1 times A. We're trying to get the A by itself. So that means we are going to apply the inverse to remove these factors one at a time. So we apply the inverse to both sides to remove that one. Same thing is going to happen here. Now note, the order of matrix multiplication matters. And finally, what we'll end up getting is this representation. E3, E1 inverse, E2 inverse, E3 inverse on U is A. And so we've managed to remove everything, and we've managed to come up with a factorization for A. But now the real magic lies in the form of this factorization. So what we're going to do is discuss this factorization form a little better. And in particular, we're going to ask, what structure does this have? Because it will have a structure. And you could probably guess, if we take a row replacement, this creates an elementary matrix, either the forward or the inverse one, that is lower triangular. So every one of these row replacement, if you're replacing rows below, so the thing that happens in the forward substitution, that's the type of replacement you're going to do. You're always going to create zeros below your pivot. Every one of these is a lower triangular matrix. So it will look something like this. It will have ones on its diagonal and some non-zero number below. Now in class, I already proved to you that a product of lower triangular matrices is a new lower triangular matrix. So that's good. I know then for sure that this matrix will be lower triangular. So it's some matrix L. But the real magic that comes out is to examine the special structure of this. So we get a little more. And I'm going to try to demonstrate this to you in our specific 3x3 case. And this will hold for other cases. You can do this with induction. There are other arguments to prove this. But let's just talk about it here in a situation that's very related to what we were doing. So our matrix L kind of looks like this. We've got a 1, 0, 0, a negative number there, 1, 0, 0, 0, 1. We've got a second matrix that corresponded to the inverse of the second step. So it was, the first step was to create a 0 under the pivot in that second row. The next step was to create a 0 there. So that's what the inverse of our second matrix looked like, and I've got the wrong subscript. And finally, this third, the inverse of the third step created a 0 under that second pivot. So it looked something like this. Now, all this is going to be an exercise in matrix multiplication. And when we just go through this matrix multiplication, something very interesting is going to happen. So we go through, if we were to perform this matrix multiplication, you can take a sec, pause it, and see, you'll end up with the following. Negative C2, negative C3, and 1. And if you were to finally do this matrix multiplication, you'd get a very interesting and amazing result. And this is all completely due to the structure of the operations we are doing. You're going to end up with a lower triangular matrix, and look at the entries. The entries here are exactly the same entries that appeared in those individual triangular matrices, in those elementary ones, in the same spot, and it preserves the structure. We are very, very lucky here. It's almost as if the universe wants this to happen. So in general, and now again, this isn't a foolproof, but in general, when you have your lower triangular matrix, if it's a bunch of these elementary matrices, and they are the inverses of the order you applied them in. This L is populated, can't spell here, populated with the CI entry and the negative of CI entry of each EI inverse in the same location. That's really, really lucky. So that when we want to actually start with a matrix and compute this, what's called LU factorization, we can do this, and we can do it in a really easy way. This LU factorization essentially comes from us applying the inverse of each of those steps that we took to get the U and just dumping them into the matrix. So what's going to happen is we're going to take our original result, we'll have the identity matrix for L, and then everywhere that we did a row operation, we will use its opposite sign. So we have a -2, a 3, and a -1, 0, 0. The U was the matrix that we got from earlier. And what this tells us is that our original matrix, the one that we started with, a dense matrix with no structure initially whatsoever, it turns out that that matrix can be factored in some strange way. This is upper triangular, this is lower triangular. These entries correspond to the row operations that we needed to do to get to this U. And so if we want to create this factorization, it's very, very easy. All we have to do is find all the EIs and then simply store the negative values in this L. Simple. Now, this example that I showed you, it holds, but it's for a very special case. It's for a special case where all we needed to do was row replacements only. In real life, we'll need swaps as well. So I won't get into the details of how you do it with swaps, but this special case sets the ground. Right? And when you do it with swaps, you're going to need what's called a permutation matrix. So you're going to have to store the order for the swaps in a special matrix here. But the point of the story is it takes this dense matrix and it writes it as two structured matrices. Why that's important and why that's useful is what I'm going to show you next.